Welcome to this talk, which is a post-recording of the talk that I gave at the 2018 American Control Conference in Milwaukee. And the title is Decentralized Robust Control of Coupled Multi-Agent Systems under Local Signal Temporal Logic Tasks. And this is joint work together with my supervisor, Professor Dimos Dimorogonas. The talk is divided into these four parts, so we will start with an introduction and the motivation of the problem. Before we then talk about signal temporal logic and why we make use of it. And then we'll talk about the main part of this talk, which is about multi-agent systems, and in the end, we'll conclude. As we all know, multi-agent systems consist of multiple single agents, and each agent has its own communication, computation, and actuation capabilities. And together, these bunch of agents, they're supposed to achieve complex tasks. And these complex tasks can range from simple spatial tasks, such as reachability, classically considered in control, over collaborative spatial tasks, for example, consensus and formation control, and in this work in particular, time tasks, so spatial tasks under given deadlines. In robotic applications, for instance, it's also of utmost interest to ensure safety tasks, for example, collision avoidance. The next natural question is, of course, how do we formulate these complex tasks? And typically this is done by using temporal logics, because temporal logics allow to mathematically express complex tasks. And then basically we get three ingredients for the problem. And we have an environment which is scattered with obstacles and goal regions. We have continuous time dynamics, here shown by omnidirectional robots. And we have the complex tasks, which will be, as we will see, formulated in temporal logics. And different scholars from different fields have been working on these kind of topics. And there's a large amount of literature on automata and abstraction-based approaches. There are game-based approaches by using a reactivity framework. There are optimization-based approaches and, more recently, learning-based approaches. And what all of these frameworks have in common is that they're computationally demanding. And what we propose in this work is a computationally efficient framework. But by stating or by motivating our contribution, I want to start with a quote from the famous textbook of Meshbahi and Egerstedt, which says that agents in multi-agent networks are required to operate in concert with each other in order to achieve system-level objectives. And the question that we asked ourselves was, what if agent couplings or uncertainties impede the agents to operate in concert? How do we detect and replan such situations? And furthermore, how do we deal with conflicting individual tasks? And what we propose is to use signal temporal logic, what I will introduce in the next slides, and derive distributed hybrid feedback control strategies. The ingredients then are that we are allowed to impose state and time constraint tasks. Since we use signal temporal logic, the framework itself will be robust and computationally efficient since it will be abstraction free. Okay, so let us look at signal temporal logic. And signal temporal logic consists on the bottom layer of so-called predicates, here denoted by mu. And these predicates mu are obtained after the evaluation of a predicate function h. And basically the predicate is true if the predicate function is greater or equal than 0 and false otherwise. We can illustrate this in an example where we assume the predicate that the norm of x at time tau should be smaller or equal than epsilon. And then we can draw an epsilon ball in the two-dimensional state space. We can draw a continuous time trajectory, and then we know that the predicate here will be true for all the times where the trajectory is within this epsilon ball. And this is what we can formalize by using the predicate function h here. So the predicate is true if and only if the predicate function is greater or equal than 0, if and only if the state at this time is within this epsilon ball. Using these predicates on the bottom layer, we can define the syntax, or also called grammar, of signal temporal logic by using negations, conjunctions, and disjunctions, and the temporal operators until, eventually, and always, which I will give an intuition on in the next slide. First of all, we can define semantics, which are not formally given over here, but this satisfaction operator here basically denotes if a signal, a continuous time signal x, satisfies the formula phi. Furthermore, we can define so-called robust semantics, again, not formally given over here, but raw phi denotes not only if the signal x satisfies the formula phi, but also how robustly the signal x satisfies the formula phi. And there's an important relation between these two. So if the robust semantics rho phi are greater than 0, it means that the signal satisfies the formula phi. And this is important to keep in mind for the remainder of this talk. So, as already said, we want to give an intuition on what these temporal operators mean. And we have the continuous time signal x plotted here in all of these plots, and we have 3 different formulas. For eventually, we can draw a space-time box here in green, and eventually means that the signal x should be in this box at least once. And this is, of course, given here. The formula is satisfied, and it's satisfied with a positive robustness. For always, however, in the 2 lower figures, we need to have that the signal is always contained in these space-time boxes, which is given in the middle figure here, but only with marginal robustness, and which is not given in the lower figure. So here the formula is not satisfied, and this is what we can see by looking at the robustness, which is negative. Okay, so let's jump into the main part of this talk. We consider M agents, and these M agents are subject, each of these agents is subject to these dynamics. And basically we have an affine intercontrol input system where Fi and Gi here are locally Lipschitz continuous, and we also have a controllability assumption on G that is stated in the paper. We do have a bounded noise acting on the system dynamics, and we have in red here a coupling term. And it is a coupling term because it depends on X, where X may include the information of all the agents of the system. And we call this red term given dynamical couplings. And the way we can think of it is that, for example, 2 agents may be connected by a spring. So if one agent moves in one direction, it will automatically be pulled, or the other agent will be automatically pulled in the same direction. So this is why we say it's a given dynamical coupling. But we can also induce dynamical couplings, here in blue, by using this control law, such that the blue term over here can be used to achieve group objectives such as collision avoidance or formation control. Okay, so these are dynamical couplings, and now we'll look at the formulas, because this control input Vi here is still left, and we will use it to satisfy signal-temporal logic tasks. We have psi formulas in blue, which consists of predicates, negations of them, or conjunctions. We have phi formulas in red, which are always or eventually. And we have theta formulas, basically a conjunction of phi formulas. And we have dealt with them by using a hybrid control strategy in our previous work. And for simplicity here, we will only look at phi formulas. And we will do this in a bottom-up approach. So bottom-up means that each agent I has its own individual task phi I. And this task phi I, of course, depends on the state xi, but it may also depend on other agent states. So on the previous slide, I introduced dynamical couplings, and this introduces formula agent couplings. And therefore, we define the stacked state vector x phi I, which contains, of course, the state of xi, but also states of the other agents that are involved in the formula phi I. In order to deal with these formula agent couplings, we define maximal dependency classes. And I want to do this here in an example for 4 agents with these 4 tasks. Agent 1 depends on agent 2, and agent 4 also depends on agent 1. So we can draw a directed graph given over here that shows the dependencies. And we say that a maximal dependency cluster is then each weakly connected component. And in this case, we see that Xi1 is one cluster consisting of this agent, and the other cluster, Xi2, consists of agent 3. And then we're ready to formulate the problem. So we look at each cluster separately, and we derive a control strategy as follows, depending on 2 cases. The first case is that all of the agents in one cluster are subject to the same formula. Then we want to design a distributed feedback control law. Here is so distributed because each agent will apply this itself. And it depends on the states contained in xi. And we want that this control law achieves a satisfaction of the formula phi I, but not only a satisfaction, furthermore we want the formula to be robustly satisfied. And this is what we achieve by ensuring that the robust semantics are lower bounded by a positive robustness measure Ri. And Ri is something we can design as a designer within some given physical limits, of course. For the other case, so if not all of the agents are subject to the same formula, we propose to still apply this controller from the first case, because as we will see, it gives a good initial guess. And on top of that, we will design a local online detection and repair scheme such that the robust semantics will be lower bounded by some robustness Ri, and Ri will be maximized. Okay, so in order to tackle this problem, we propose a distributed prescribed performance controller, which is given over here. And I will not go into details, therefore I invite you to look into the paper and to also see the proof. But the intuition is given in this figure over here. So the red lines define what we call lower and upper funnel. And these are design parameters, so to say. And our goal is to confine the robust semantics of psi within this funnel. And this is achieved by this distributed feedback controller. So raw psi will be confined in this funnel, and by the design of the funnel, considering the robustness Ri, we will make sure that phi I will be satisfied with a given robustness. The intuition that I want to give here is that epsilon I goes to infinity as the robust semantics approach the boundary of the funnel, while this term over here gives the direction in which the robot needs to steer in order to go more into the interior of the funnel. This controller, or we can show that this controller, under the assumption that all the agents have the same formula, all the agents can communicate in this cluster, and they share the same PPC parameters, which means they have the same funnel. And then we can guarantee that the formula phi I is satisfied with a robustness Ri. What happens in the case if these assumptions that all of them are subject to the same formula does not hold? And with respect what I emphasized in the beginning, if we have uncertainties or if the agents do not operate in concert, this may happen, and then this controller may become singular. And what we propose then is an online detection and repair scheme. So in the first step, we detect these events simply when the robust semantics hit the funnel boundary. And then we propose a 3-stage repair procedure, which is expressed as a hybrid control strategy. This strategy is not formalized here in this talk, but again, I invite you to look into the paper. I'll try to give an intuition on the 3 repair stages. The first repair stage happens locally. So if a critical event here is detected, then the funnel will be relaxed. So the funnel will be made a bit broader. And we give the agent another try to satisfy the formula. And here in this example, we can see that this works. But it can also happen that the agent will again, so to say, the robust semantics will hit the lower funnel, and then we will move on to the second repair stage. And this repair stage applies under some timing conditions. And these timing conditions are basically if all the other agents that are involved in the formula of agent I can postpone their own task. And then they collaboratively use the controller UI and use the control guarantees that we derived in for case A, which will lead to a satisfaction of phi I. If this second step, however, does not apply, we will again locally reduce the robustness Ri to find least violating solution. And this hybrid control strategy then results in that the robust semantics will be lower bounded by some robustness Ri, and Ri is either positive or maximized. And in order to have well-posed solutions, we also guarantee that Xeno behavior is excluded. In the paper, we presented simulation results, but in the meantime, we performed some real experiments where we run our code on omnidirectional robots, and we modeled these omnidirectional robots by these dynamics. So we have bounded noise, and we, on top of that, included induced dynamic couplings in blue to achieve collision avoidance of the agents. And this is done by means of a potential field. The experimental setup then is the following. So we have here denoted in green by MO moving obstacles, so just robots moving around. And the robots of interest are R1, R2, and R3. And they're subject to the following tasks. So robot R1 and R3 are supposed to go to region A2 and A1 within some given deadlines, respectively, while agent R2 is supposed to stay epsilon close to the two agents. And this is of course not possible, so the least violating solution that we will find is to stay in the middle. After that, the agents will regather, and then the next scenario is that agent R1 is supposed to go to A3 while staying close to agent R2 within some deadlines, while on the other hand agent R2 is supposed to go here. So they will need to establish communication to satisfy the task here together. And this is what we will see here in the movie. And the moving obstacles start moving around, and we can see directly in the beginning that the collisions are avoided by the induced dynamical couplings. Agent R1 and R3 go to their respective regions within their given deadlines, while agent R2 stays in the middle, finding a least violating solution and staying as close as possible to both of these agents. After this, the agents will regather in the middle, and what we can see here again is a collision avoidance that works pretty well. After this regathering, agent R1 is again supposed to go to this region and stay close to the agent R2 in the middle, while agent R2 is supposed to go here. So they will at some point establish communication when a critical event is detected, which happens here, and now they will collaboratively use this distributed feedback control law, and this will lead to a satisfaction of the formula, as we can see here. So they're going into their respective regions while staying close. After this satisfaction, the agent R2 will continue with its own task, and this means going to region A4, here again avoiding collisions, but eventually reaching this region over here. Okay, so what we now look at is at the robustness or robust symmetrics and the funnel for the last scenario for the second agent. So the second agent was supposed to go here, but it was asked for help, so it collaboratively helped to satisfy this task, and after that the agent then satisfied its own task. And this is what we see here. So initially there's no problem, no critical events, but then the agent 2 is asked to help, so it gets the information or the funnel of agent 1. And as we can see here, we have some more critical events due to collision avoidance issues, which reduces the robustness. But eventually the formula is satisfied with some robustness. After that, the agent continues with its own formula, and we see more critical events due to input limitations and here again due to collision avoidance. And this then leads to a reduction of the robustness, but eventually we again have a satisfaction of the formula with a negative robustness though. By this I want to conclude my talk. What we presented in a bottom-up approach is an abstraction-free and computation-efficient framework that is also robust. And it's especially robust in two levels. So with respect to additive noise acting on the system dynamics and with respect to the satisfaction of the task. For future work, we want to account for the input limitations and for the dynamics, because in the paper we have a controllability assumption that we want to relax in the future. We also want to enlarge the STL fragment under consideration by using higher level decision-making layers, such as sampling-based RRT star and reinforcement learning.